Hello students, in previous lecture we have studied the concept of closed set and we proved that every closed sphere is closed set. So we'll take the second session on closed sets. So just like as open sets, we'll prove the important result about closed sets. Let XD be a metric space. Be a metric space. Then 1 phi and x are closed in X. Second, arbitrary intersection of closed sets is closed. Arbitrary intersection of closed sets of X is closed. Third, finite union of closed sets in X is closed. So proof 1, since phi complement is equal to X and X complement is equal to phi are open in X. We know that the given set is closed if their complements are open. If their complements are open, implies phi and X are closed in X. Second, let F alpha belongs to index set, be family of closed subsets of X. What is our aim? Intersection of all those sets F alpha belongs to index set is closed in X. Okay. For this, we have to show that its complement is open. For this, intersection of F alpha belongs to index sets, its complement is same as union of F alpha complement alpha belongs to index set by De Morgan's laws. Okay, so we'll give this for 1. Now, each F alpha is closed implies each F alpha is open set in X. Since arbitrary union of open sets is open, arbitrary union of each F alpha complement is open. Arbitrary union of open sets is open. Therefore, union of F alpha complement alpha belongs to index set is open set in X. And therefore, from 1, intersection of F alpha complement, full complement, alpha belongs to index set is open. Therefore, its complement, intersection of F alpha, intersection of F alpha belongs to index set is closed. So thus we proved that arbitrary intersection of closed sets is closed. Now we have to prove that finite union of closed sets is closed. Third, let F1, F2, dot up to Fn be closed sets in X. Sets in X. What is our aim? Union of Fi, I is equal to 1 to n, is closed in X. In X. So for this, union of Fi, I equal to 1 to n, its complement is equal to intersection of I equal to 1 to n, Fi complement by De Morgan's laws. De Morgan's laws. For this again we will give 1 here. Now since each Fi I equal to 1 to n is closed set, implies each Fi is open set. Fi complement is open set. Right. Since finite intersection of open sets, intersection of open sets is open, therefore from 1 or therefore intersection of Fi complement I equal to 1 to n is open, and therefore by 1 union of Fi complement I equal to 1 to n is open. As this set is open, therefore its complement is open. Therefore union of Fi I equal to 1 to n is closed. So we proved that in any metric space XD, empty set and X are closed. Arbitrary intersection of closed sets of X is closed, and finite union of closed sets in X is closed. Okay. Now here we will prove finite union of closed sets in X is closed. So note note arbitrary union of closed sets in metric space XD need not be closed. Justification: for every n belongs to n, if I take in set is equal to 0 to 1 plus 1 upon n close. Is closed in RU. Every closed set, closed interval is closed. Right. What is your I1? 0 to 2. What is I2? Arbitrary union. If I take union of these, sorry, 1 minus 1 by n. 1 minus 1 by n. What is our first set? I1 0 to 0. 0 to 0, that is singleton 0. What is I2? closed interval 0 to half, then 0 to 1 by 3 and so on is closed. Now union of ion n is equal to 1 to infinity is equal to union of 0 to 1 minus 1 by n is equal to 1 to infinity. This is nothing but limit n tends to infinity of 0 to 1 minus 1 by n. If I take I1 union I2, it is I2. Union of three intervals is I3. And so on, as n tending to infinity, it becomes this set, which is nothing but 0 to, as n tends to infinity, this is 1 minus 0, which is nothing but close open interval 0, 1 is not closed in RU. So, arbitrary union of closed sets need not be closed. Is it clear? Now we'll take the result that every finite subset of any metric space is closed. Okay. So take the example. Let XD be metric space, then one any singleton subset of X is open, any singleton, then subset of X is open, and second, finite subset of any finite subset of X, is open. Okay. So solution, we have to prove that singleton subset. Okay. So for X belongs to X, let X be singleton set. Claim singleton set X is closed in X. Okay. If singleton X is equal to X, then it is closed. If singleton X is proper subset of X, then to show singleton X complement, which is X minus X, is open in X. So we'll take, let Y belongs to singleton X complement. Then d of xy is equal to r greater than 0. It must be greater than 0. Okay. In this case, open sphere about Y. A set of Z belongs to X such that d of zy is strictly less than r, doesn't contain X, and therefore SRY is subset of singleton X complement is equal to X minus X. Okay. Thus for every y belongs to X complement, there exist r greater than 0 such that, what is that r? D of xy, such that s or y belongs to, is contained in singleton x complement, and therefore singleton x complement is open set, which implies singleton x is closed set in x. Now we have to prove second part. Any finite subset of x is open. Second, to show any finite subset of x is open, closed. So let A be finite subset of x. Case 1, if A is equal to phi or A is equal to singleton x, then A is closed. Suppose, case 2, suppose A is equal to set containing x1, x2, dot dot xn, n greater equal 2. Then A is equal to union of singleton xi, I is equal to 1 to n, where singleton xi is closed for every I, is closed in x. Now since finite union of closed sets is closed, finite union of closed sets is closed, therefore A is equal to union of xi, I equal to 1 to n, is closed in x. So we proved that every finite subset of any metric space is closed. The next example, let XD be metric space. Okay. Prove that every subset of x is closed. Prove that every subset of x is closed if and only every singleton set is open in x. Is opening x. In additional, deduce that every set is closed. Deduce that every set of x is closed if and only every subset of x is open. X is open. So solution. Suppose every subset of x is closed. Every subset of x is closed. If I assume that every subset of x is closed, then for x belongs to x, singleton x complement is equal to x minus x is closed in X. Implies singleton X is open in X. Open in X. Conversely, suppose singleton X is open in X for every X belongs to X. Claim every subset of X is closed. Every subset of X is closed. So let A be subset of X. A be subset of X. Then X minus A is subset of X. X minus A is subset of A. Right? X minus A is equal to union of singleton Xi's, where Xi belongs to X minus A. Since arbitrary union of open sets is open, arbitrary union of open sets is open, implies X minus A is open, and therefore A complement is equal to X minus A is open. This is your A complement is open, and therefore A is closed. Thus every subset of X is closed. Every subset of X is closed. Right? Deduction now. Every set of X is closed if and only if every subset of X is open. Okay? What we have to deduce? Now, suppose every subset of X is closed. Claim every subset of X is open. X is open. So let A be subset of X. Then A complement is subset of X. By hypothesis, A complement is closed. A complement is closed. Therefore, A complement its complement is equal to A is open. Okay. Now, thus now suppose every subset of A X is open. Claim every subset of X is closed. So let A be subset of X, B A subset of X. Then A complement is also subset of X. By hypothesis, A complement is open, which implies A complement its complement is closed. So we are selecting arbitrary subset. As its complement is open, therefore it must be closed. So thus this result is proved. Now we'll take one more example. Example, let XD be matrix space and AB be subsets of X such that A is closed and B is open. A is closed and B is open. Show that A minus B is closed and B minus A is open. Okay, so simple. A minus B is same as A intersection B complement, where A is open, A is closed, B open implies B complement is open. In finite intersection of finite or intersection of open sets is open. Is it right? Sorry, B is open, therefore B complement is closed. So what we proved? Intersection of closed sets is closed. Implies A intersection B complement is equal to A minus B is closed. On same line, what is your B minus A? Now B minus A is equal to B intersection A complement, where B is open and A closed implies A complement is open. Now we know that finite intersection of open sets is open. Okay. Now since finite intersection of open sets is open, therefore B intersection A complement is equal to B minus A is open. So thus today we have studied the concept of closed sets, theoretical part on it, and we have taken also some few examples which are also theoretical examples, so that you can use that examples as well as theory while showing subsets of given matrix space are closed or not. So with this discussion today we'll stop our session. Again, I request watch each and every session on matrix space, because all these sessions are very useful for study of NET set examinations. Thanks. Bye bye.